And I think we are live. Uh, Welcome everyone to another Packt live session. Today I'm joined by Ashish Ranjan, author of Mastering PyTorch, and we'll be talking about PyTorch and deep learning. And during this session, we will be giving away two e-copies of Mastering PyTorch to two lucky winners. You can see the ticker below. So comment with #Packt to enter the raffle. And also add your questions to the chat, and we'll try to go through as many of them as we can. So just if you could just drop in a comment to let us know we're live, that would be useful. Oh, excellent. So, Ashish, would you like to tell us a bit about yourself?
Sure, Bhavesh. Firstly, thank you for organizing this. And thank you for everyone who is joining this event from all different time zones. My name is Ashish. I am here to speak about this book I wrote and published recently called Mastering PyTorch. It's actually a second edition of this book. The first one came out about 3 years ago or 3.5 years ago. And just a bit on myself. So I am a machine learning engineer, data scientist, currently working as head of machine learning at a construction tech startup, XYZ Reality, based in London. And yeah, I'm really excited to discuss not just about the book, but about PyTorch, about deep learning, about AI in general for the next hour.
And if anyone's got a question for Ashish, just drop it in the chat there, and
Sure.
we'll try and answer as many as we can. So my first question will be, why should we use PyTorch for deep learning?
Yeah, I mean it's an interesting question, right? Like to answer this, I would take an analogy of a programming language per se, right? So a lot of data scientists, machine learning engineers, I would say a large majority use Python. And so if one were to ask the question, why should we use Python for data science, machine learning? If you ask me that question, I would say the ease of use is perhaps the biggest thing that goes positively for Python, that enables people to just quickly prototype stuff. And a machine learning engineer, a data scientist, a statistician doesn't want to perhaps know the depths of compilers and how assembly language works and so on. So to take that analogy to now deep learning frameworks, PyTorch, I think the biggest reason why it is being used right now mostly for deep learning is its ease of use. So when I say ease of use, PyTorch is a Python library. So the ease of use comes from it being very Pythonic. And again, to go a little bit in the background, in the history of things, people must be thinking about TensorFlow right now. Like, why not TensorFlow? That's also Pythonic and so on. So TensorFlow came out around 2015, 2016 as one of the first standard deep learning frameworks. At the time, the whole landscape was pretty fragmented. There was, I don't know if many of the viewers, listeners today were into machine learning AI back then, but I was, and I was working on this library called Theano, which came out of Montreal, and there were like few libraries here and there, and one of such libraries was also Torch, written in this scripting language Lua. It has existed since 2002 actually, but there was very little ease of use because Lua as a scripting language wasn't really familiar to people doing machine learning data science. And so I think while TensorFlow came into existence, it was a bit daunting for developers in its first version because of the, I don't know if people remember the first version APIs of sessions, the TensorFlow session, the computational graphs. It was very mature as an engineering product, but still not very easy to use per se. And then developers within Meta, back then called Facebook, were trying to develop PyTorch, which should use Torch, but like instead of having bindings of C++ on Lua, having bindings of C or C++ on Python. And so the key difference that arose was they really wrote this library keeping those users in mind, the ease of use in mind, and it felt like it's written with Python in the forefront, as opposed to TensorFlow, which was written by Google Brain with like really mature engineers, keeping the performance in mind. So yeah, I mean, in short, one of the major aspects that goes for PyTorch for using for deep learning is its Pythonic nature. And on a more technical side, I just spoke about computational graphs. So from the very beginning, PyTorch has used dynamic computational graphs, which means that while you are defining and trying to run a deep learning model, deep learning models are usually composed of layers. The dynamic computational graph allows you to run everything up to the current layer that you have built so far. You don't have to complete the model, compile it, and then wait to pass some data through it to basically examine what happens. So this allows for very dynamic interaction with your models while you're building them, and also makes way for very easy debugging. So yeah, I mean, these are like at the foundational levels, the big reasons. I will say it has continued to be a major deep learning library also because of the community. So there is the PyTorch forum, but there is also the PyTorch ecosystem. So there is a, if you Google PyTorch ecosystem, you will see a web page on the Torch website which shows you at least I would say 50 different third-party libraries which are working closely with PyTorch. So this includes something like an Optuna, something like a PyTorch Lightning, something like Captum. All of these are adhering to different use cases within AI or different verticals within AI, and they are easily plug and play able with PyTorch. So I would say the community goes in favor also, right? I can feel as a PyTorch developer myself, I can feel that there is a lot I gain by just interacting with the ecosystem. And internally as well within PyTorch, there is Torch Vision, which encompasses everything around visual data, visual models. So everything computer vision. There is Torch Audio, which has all kinds of functions to handle audio data and basically building any kind of audio processing models. And then there is Torch Text, similarly for the textual world to basically easily handle text data and so on. And so that's another like internal suite of libraries within PyTorch that really establishes different modalities very well. One more thing on the advantages of using PyTorch would be the interoperability, the easiness with which you can take the PyTorch model, let's say convert it to an ONNX model, which is the I would say I mean, it stands for Open Neural Network Exchange. So it is the universal framework from which you can convert to or convert from into different formats. So you can go from PyTorch to TensorFlow models seamlessly. So my point is, at least the entry point towards building or training a model, PyTorch really seems to be the framework of choice. Maybe for deploying, you want to go to a different library or a different route, and there are so many options. We can talk about that. But just for starting off and just building things, PyTorch definitely sounds like the library of choice for deep learning.
We have our first user question. So, how do you suggest going about the book? What should we focus on while reading Lost in PyTorch?
Great
Something like
question. Great question. And as an author of the book, I this is how I thought of the structure of the book, right? So I have the book right next to me, by the way, just so you know. I'm gonna show it to people just for those who haven't had a look. It's quite a big book. And so there are parts to the book, I would say, implicitly, and like the chapters 1 until chapters 6 are more of it's not theory. Nothing in the book is theory, because every single chapter involves code and exercises that one can engage with and do some hands-on learning with. but the chapters 1 to 6 are the more theory part, if you will, within the book. So they talk about a different range of neural network models, so ranging from CNNs to RNNs, LSTMs, and transformers, which are the current hype. And then graph neural networks is something we have added in this edition. So if you want to have a comprehensive understanding of deep learning architectures and how to go about them using PyTorch, that's the first part. And if I were to study deep learning, or like just revise my knowledge of deep learning, I would start with something like that. The next part, from chapters, I would say 7 until roughly chapters 11, these are more on the applications of deep learning. So it ranges from, I think, music and text generation, neural time, style transfer, GANs, diffusion, again a new addition to this edition, which is also a recent phenomenon, and deep reinforcement learning. So all of these are applications of deep learning, and these chapters are more fun to engage with. And these exercises are really something you can even use as a template for whenever you want to build something on top of any of these applications, and in fact use these same principles or same building blocks to then work on a similar task. So maybe not text detection or text classification, but maybe text generation, but using the same building blocks. Then there is a third part, which I have received the most positive feedback from for the first edition, which is all about the engineering, the machine learning engineering, or the deep learning engineering. Some people may call it ML ops. So that goes from chapters 12, I would say, to chapter number 14. So that covers training optimizations. How do you make training fast? How do you train really, really large models on PyTorch? That also involves the deployment of models. So how do you deploy your model on cloud, on different kinds of configurations, and how do you optimally deploy your models? And then also includes how to deploy your models on the edge, just like the mobile devices, for example, Android or iOS. And this edition again has a brand new chapter focused only on how to deploy PyTorch models on either Android or iOS end to end. So building basically AI applications as Android apps or iOS apps. There is a fourth part, which is all about the ecosystem. So I speak about how can you rapidly prototype PyTorch models. Not everyone wants to write the raw PyTorch code. Sometimes you just want to quickly have a sense of, can I use this data for this task? So there are libraries such as Fast AI or PyTorch Lightning. They abstract away a lot of details and are still very useful to solve your problems. I speak about PyTorch profiling in that chapter as well. Then there is an aspect called AutoML. So there is a library called Optuna, which helps find the most optimal hyperparameters. And Optuna is an example of one of those PyTorch ecosystem libraries, which is used widely by many, because you don't want to run a grid search yourself. You just want to maybe import Optuna and then set up a search session, get this search session to give you the best model hyperparameters for your model. Then there is interpretability. So there is Captum, another part of PyTorch ecosystem, which helps you understand how your models are working, which is getting more and more difficult as we get into more and more advanced models. But for something like CNN models, it's really useful to see what are the saliency maps. For example, is my model actually learning the patterns it should, or is it just coincidentally performing well, learning on noise, which sometimes could also be overfitting. And then I have two more chapters towards the end, one on recommendation systems with PyTorch. Here I just use vanilla PyTorch to show how we can build a recommendation system from scratch. And I would say the cherry on the cake literally is the last chapter, which is PyTorch and Hugging Face. This chapter is really, this being the last chapter, is really very symbolic of the field of AI right now, because I feel, compared to 3 years ago when the first edition came out, today a lot of things in AI are being abstracted out. And Hugging Face is a great example of a company, of a community, where you have different data sets and models and services, so to speak, or spaces available for you to run. So today very few people are building anything from scratch. They are usually picking things from somewhere and then building on top of that. And the sheer depth of integration between Hugging Face and PyTorch, I would say, is also a huge reason why PyTorch is becoming more and more prevalent as a deep learning framework. And actually, I forgot to mention when you asked me, Bhavesh, about PyTorch being a choice for a deep learning framework, is also because that it was being spearheaded by Meta, the company, but in 2022, I guess people who have been following PyTorch should have known that it is now part of the Linux Foundation. And so now there are, if you go to that page, if you just search for PyTorch Linux Foundation, you will see there are premier members. I think that premier members include all the cloud providers: AWS, GCP, Azure, of course Meta, and it also includes Hugging Face, it also includes Nvidia. What it means is all of these companies, all of these major AI players today are contributing directly to PyTorch, or they are building AI tools which are fully compatible with PyTorch from day one. So this is another huge reason why using PyTorch perhaps keeps you relevant in today's day and age of AI, which is growing insanely fast. So by the time this session ends, I don't know which company would have released which version of an LLM that would have beaten all other LLMs. So hopefully that answers the question as well.
Yeah, I think that's a comprehensive answer as well on the content of the book. Pablo's got a question as well. So which is the most powerful feature of PyTorch?
The most powerful feature of PyTorch, I am trying to, like, there is a strong tie between two things. The first is ease of use. So give me any problem, I will find a way to solve it using PyTorch much quicker than I would do with TensorFlow or TensorFlow plus Keras. A, because of the easy syntax, easy to understand, and B, because there is a plethora more of tutorials or discussions blogs available written in PyTorch. So just a fun fact there. Bhavesh, actually take a guess. How many repositories do you think today are using PyTorch on GitHub?
Oh, 50,000.
50,000. You're quite far away. So that more than 600,000 repositories on GitHub are today using PyTorch. It's a sign of this becoming very prevalent. So it's very easy to find relevant resources around anything to build within PyTorch. That's one. And the second thing I would say, the being the most powerful feature, is also the integrations on different levels. So the integrations with, as I said, Hugging Face is a huge game changer because you can start building off of existing stuff. You don't have to reinvent the wheel. It's very tightly knit and very tightly integrated there. But also on deployment side, it's very well integrated with different runtimes. So ONNX runtime, OpenVINO, via the ONNX route. So Hugging Face Optimum, and we will talk about these things maybe on a separate note. But just the topic of interoperability with PyTorch on other frameworks, both during training but also during deployment times, is another genuine reason why I feel much more comfortable when I'm building with PyTorch. I mean, I'm not, again, not trying to like put down TensorFlow, but it's my genuine feedback that when I am working with PyTorch, I find it much easier to find relevant resources to continue off of as compared to TensorFlow, at least during training, at least while building the model. And while deployment could be a different story on both cases.
Uh, Pablo, I hope that answers your question. So I've got a question on, so what are the benefits of combining different deep learning architectures?
Combining different deep learning architectures. Okay. Um, So there is, in machine learning, there has been this practice called ensembling. It has always existed, which is bringing together of different models. So combining of different deep learning architectures or deep learning models could be seen in multiple ways. So are we talking about sequential stacking of them one after the other, or are we talking about having an ensemble of different models that produce us a final output? So one thing is, I am a big fan of still using different architectures for the different values they bring. So transformers today are hands down the most popular and the most valuable deep learning model architecture that we have ever seen. But I firmly believe, and maybe it's a hot take, but that's not the optimal. We are yet to see more improvements in the future. That improvement could look just like totally different from what we have seen so far ever, or it could be a mix of things from before. It could be a reincarnation of LSTMs. It could be a reincarnation of CNNs plus transformers. Who knows? So it is just as an academic point. I would say there is a lot of merit in trying to combine different architectures. Now, to go into a little bit of the hows of how do we do that today, I would say like the encoder decoder framework, which is very popular now, uh, is implicitly telling you that there is a sequential combination of two different deep learning architectures. I'll give you an example. Actually, in the chapter number 4 of the book, or chapter number 3 rather, the chapter is called Combining CNNs and LSTMs. And this chapter is basically taking an image and generating caption for that image. So it's like I take your image and I have to give a caption, a subtitle to that particular frame. How do you do that? Firstly, you will need some kind of a visual model, so a CNN model, let's say, to convert the image into numbers, into embeddings. And then to generate text, you need some kind of a text model, so could be a recurrent net. In our case it was LSTM, so we take that embedding and then we pass it through a decoder. So the first part is the encoder, the CNN, and the second part is the decoder, the LSTM. So that's a classic example of encoder decoder, but this happens everywhere. And this is tightly linked to the other reason where having or combining different architectures makes sense, which is multimodal models. I guess many people are more and more hearing to this, like this phrase multimodal modeling, multimodal data, which is to say that we are now operating in this paradigm where we don't just need one model for text, one model for audio, one model for video, one model for images. We want a model which can do everything. So when you say I want one model which can do everything, it sounds like you want to have different architectures within your big model catering to those different modalities. So example again could be you want to take a video and you want to output the subtitles automatically runtime, very similar to what I said before. Or you could want to take text and generate an image, that's diffusion for you. So that's again two kinds of models. So one taking the text, encoding that into some numbers, and then the other side is basically taking some random noise as a starting point and these numbers and generating a real looking image, that's diffusion for you. So yeah, I mean, combining of architectures on the sequential side, the encoder decoder, that's very prevalent today and we are doing a lot. But also on the parallel side, so like having multiple models taking a go on your task, and then then they get together to give you the final result. Actually, a great example of this is today's LLMs. So whenever if you look at the fine print of all of these new releases of GPT-4 or Sonnet or from Claude or Mistral, most of them are mixture of experts. So they in turn are also trying to train different models and potentially different architectures, maybe slight differences but still different architectures, which are catering to different aspects of the task, and then they are coming together to give you the final answer. So combining different architectures, I would say, is definitely here to stay. And again, in the book, besides chapter 3, which is literally called Combining CNNs and LSTMs, we also have the combination of two wildly different architectures in chapter 9, where we speak about GANs. Because GANs, the full form is Generative Adversarial Networks, and it contains generative but also discriminative networks. So generative network could look like a UNet, which is a very different looking architecture compared to a discriminative model, which could be just a CNN model with some convolutional layers followed by a fully connected layer. And that's something we go and build end to end in chapter 9 for those who are interested to have a look.
Excellent. We'll take one more question before we do our
Yeah,
first
sure.
draw. So Ronald mentions, are there any advantages of using deep learning for tabular data? or is gradient boosting still the king?
I keep reading up on this. So I personally haven't really seen a strong use case where deep learning has aced. Like, okay, I do read papers every now and then on transformers, beating gradient boosted trees on some particular task, on some particular data set. But by and large, for me at least, if you were to ask me what would you use, and I would hands down use gradient boosting for that task. And this is again an example. I was actually this we should use this also for combining of architectures, because maybe the deep learning models can do a great job at processing raw natural occurring data, but then you can hand that processed output into something like gradient boosting. I think, yeah, the decision trees are, it's a different paradigm altogether, right? To solve the problem, it's coming from this expert systems field of AI. And I feel, just like, in terms of the paradigm of how the data looks, the tabular data looks, it's just meant to perform better with decision trees as compared to deep learning. For sure, we could, like, we could use a jackhammer to put a stapler into a staple into a piece of paper. But I mean, we could solve it better with a transformer model, but for sure that's suboptimal as of now. And I would not use deep learning for tabular data yet. I do not use it, at least.
So let's do our first raffle draw. I'll say, if anyone who hasn't entered yet, type in hashtag Packt. And I'll just quickly. I'll just quickly start the draw. So the winner is Pablo. So yeah, if you're happy, yeah, congratulations. Yeah, if you're happy, just message me your email address and I'll get the e-copy to you as soon as I can. Okay. So, oh yeah, and then people feel free to keep adding questions into the comments. So, got another question for you. So, what method can we use to speed up model training?
Oh yeah, I think that's a that's a brilliant question for anyone who is doing AI or ML. So you genuinely ask this question to yourself every time you either hit the limit of resources, or in general, if you want to just optimize your training. Guess what? We have a fully dedicated chapter to this, chapter 12, which is literally called Model Training Optimizations. So the highlights basically within PyTorch. First is, I mean, guess what? Nvidia is the largest publicly traded company in the world, and the biggest reason for that is GPUs, if I am not wrong. And the answer number one is indeed GPU. So if you really want to uh, increase your model training speed, or really want to uh, have a 5x 10x, like a huge reduction in training time, most of the cases, except for things like RNNs or LSTMs, GPUs might be the best answer for you. So being able to use GPUs with PyTorch, and PyTorch again, I think it's also one of the reasons of its ease of use. It's incredibly simple to just use CUDA under the hood with PyTorch, and not just within the PyTorch framework, but also in the Torch script, which we'll get maybe to later frameworks. So yeah, number one is GPUs for sure, and maybe TPUs from Google, tensor processing units. So just the hardware level, if you have access to them. Now, not everyone may have access. So distributed training is a big theme in that chapter. So trying to use your resources maximally. You might have CPUs, multiple of them, and your model training might be using only one CPU core, and you could be able to parallelize your training, again depending on your model architecture. But you don't have to worry about the internals of how to distribute it. Why? Thanks to torch.distributed API. So if you again go to this chapter, and if you want to dig deeper, go and Google torch.distributed. You will see plethora of examples and APIs around this, to use not just on CPUs, actually also on GPUs. If you have multiple GPUs, So the key ideas on two sides. One is the data loading and processing. So it basically helps you to load your data patches in parallel ways, so that different um, like different copies or different CPU cores are looking at different pieces of data and then bringing together the intelligence to one node. And then the model itself, that's the second part. So basically how it works more or less under the hood is you have copies of model coming together on different cores or different GPUs, doing the forward pass and uh, calculating the gradients, and then these gradients are then shared to a master node where they are averaged, and then there is a unified backdrop, and then the model copies are updated accordingly. So all of this is taken care of by this one API. It makes everything look very simple. Um, on top of this, so if this was not enough, because this could still be like maybe 4 to 5, maybe 10 lines of code to get all of this sorted, which you will see in the chapter number 12. If this was not enough, there is something called Hugging Face Accelerate library that reduces those 10 lines into literally one. You just invoke accelerate, and it does all the magic for you. Chapter 19, where we are discussing PyTorch with Hugging Face, we have a full blown section just on the Accelerate library, how it works, how it is used with a working exercise. I hope if you get a chance, you will be able to see that, and you should utilize that. I mean, that should become part of your workflow, so that at least you're just maximally using your resources, be it CPUs, be it GPUs, either on your machine or on the cloud. So those are the two main things on how to get maximum usage of your resources. I would also just like to highlight a few things on the Torch data loader itself. So PyTorch usually has its own dataset object and its own data loader object. You will get to know either all of this in the book, or you are already familiar with this. And then you can also parallelize the data loading mechanism across workers, because data loader has this num workers parameter. People usually forget to do this, and sometimes the model training, so the forward pass, the calculation of gradients, the back propagation, it might not be the bottleneck. The bottleneck might become the IO, the loading of this next batch of data and then the next batch. So to basically optimize the loading of data, the network IO on the data loading, basically this is another key aspect which sometimes helps, because sometimes the data itself is heavy and the model is lightweight. So you have to kind of analyze. And to on this point of, hey Ashish, how do I analyze which parts are suffering, like what is causing my entire training to slow down? So that's where the torch.profiler comes into play. And again, I don't think the chapter where I have placed this is chapter 15, which is called Rapid Prototyping with PyTorch. Might not be the best place to place this topic, but we have a full blown section in this edition. So make sure you check out torch.profiler torch.profile, sorry, the profiler for PyTorch, within chapter 15 or on the Torch website. It basically gives you amazing visuals and amazing logs on exactly where is your model slowing down. Is it the data IO? Is it the model itself? If the model, is it the convolutional layers? Is it the feed forward or the fully connected layers? Every layer by layer, you can basically know that, not just the latency, but also the memory consumption. So you can also see where, if for example your model training consumes a lot of memory, and it's just getting a segmentation fault error because it's hitting the maximum RAM you have. Again, you can use profiler to see where is the memory consumption the highest, and you can then play around or work around it to combat that particular issue. So I think these are some ways. There is also something called mixed precision training, especially for GPUs. So the idea here is, usually all parameters of a model, of a deep learning model, are represented in float 32. The argument is we might not need 32 bits to express every single parameter, and instead we could use float 16. So we are compromising the depth of information or the precision of information by reducing the number of bits to express weight. And that basically leads to freeing up a lot of memory, because now you have halved the size required to hold the same network parameter. And while training, that makes a lot of difference, both in speed and in memory. So mixed precision training is a hot topic. Torch provides easy APIs to use this again through torch.cuda.amp. And again, good news for you, under chapter 12, model training optimizations, we have a new dedicated section for mixed precision training. And hopefully, if you go through that section and through the exercises, you should be able to use AMP in your workflows as well. I guess that covers more or less on the MLE side, right? Like engineering side of things, how to optimize your training. If you were just to ask me as a data scientist or as a researcher, I think some of the common things to just mention quickly are, don't forget to use learning rate schedulers, because just using one learning rate in today's day and age is very suboptimal to get your models trained quicker. So try to use schedulers. Again, Torch has incredible documentation on this, and in our second edition we use schedulers in every single exercise. I feel might be wrong on that, but if I'm not using, it's my bad. You should use schedulers. And on the optimizers, try to use the Adam optimizer, for example, if you're using something older, or Adam W, again something we use in the book most of the times. So all of these things basically also help you converge quicker. So sometimes it's not the engineering advances that help you as much as just you thinking about the problem yourself and trying to optimize more as a researcher. So wearing the researcher hat for thinking on this versus wearing the engineer hat.
I just have a quick question on the Hugging Face Accelerate. Is that just for use on transformers, or can you use that for any deep learning model?
So Hugging Face is basically, like there are some misnomers here, right? Hugging Face has its own library called transformers, which is, it has all the APIs to support transformers and all text processing works. But Hugging Face in general is catering to everything deep learning. So Accelerate works on everything. So any kind of model that you may have, especially with PyTorch. I have not tried, honestly, Accelerate with TensorFlow. So at least with PyTorch, no matter which model you're trying, and the chapter that we have the examples on, chapter 19, I am actually using a convolutional net, and we do get a huge speed up in model training using Accelerate. It basically figures out and does all of the things I mentioned about torch.distributed under the hood, and it's just like one line of decorator on top of a function. It's beautiful how it works.
So, got another question for you, and I think you sort of covered it a bit earlier on. So, what are the best ways to productionize PyTorch models?
Sure. So we discussed training, and now we go to the next part, right? I think it's a great way to cover both of the options. I'll try to think of this more as a machine learning engineer, right? So you have already trained your model, you have tested it on the notebooks and blah blah blah. The first question you need to ask yourself is, do you want to deploy this as a PyTorch model object, or do you want to maybe convert this into a different format? I recommend considering Torch script for a just-in-time compiled format of the same model. What it means is, it basically forces us to go through the pathways of the model. So there is this method called torch.jit.script. Scripting is the way of converting that PyTorch model, which is written in Python, with the class definition and so on. It converts that into an intermediate representation, which is basically agnostic of Python, firstly. So now this object can be taken anywhere and loaded independent of the language. So if you were to load this in a C++ environment, Torch script does that job for you. We discuss all of this, by the way, extensively in chapter 30, which is literally called operationalizing PyTorch models into production. So yeah, Torch script to basically export these models into a IR, intermediate representation, which basically makes the model more efficient, or even ONNX. So just a universal format. Why I am saying ONNX is because once you have it in the ONNX format, now you can take it to any different format you want. TensorFlow, right? You can go for native TensorFlow and followed up by the ecosystem, and I would say rich ecosystem of TensorFlow deployables as well, such as TensorFlow Lite for mobile devices, right? TensorFlow JS if you want to put your model into a web browser, right, running in JavaScript. So that's a path. And also ONNX in itself has gathered a ecosystem of sorts of runtimes. So runtimes are basically environments in which your model can run for inference. ONNX runtime is itself now a huge entity. I think it's developed by Microsoft today. It's fully like adopted by Microsoft, the team, and the work is being done there. Excellent work's being done on basically optimizing the model for the use case that you have. So you could convert your PyTorch model into ONNX and then to ONNX runtime. Similarly, from ONNX, you could go to a slightly different route of OpenVINO. It's another runtime developed by Intel. I have used both of these, and I am assuring you that it does make a huge difference on your model performance when you go live. And basically, under the hood, what they are trying to do is, in the end, all of your deep learning models are a bunch of matrix multiplications followed by some non-linearities. So they look at the entire graph and they try to make optimizations. So anything that's redundant, they try to reduce the redundancies and make the model much faster, especially geared towards the hardware. So they might do different set of operations on your model if it was to be deployed on a drone versus if it was to be deployed on a mobile versus if it was to be deployed on the cloud being the most common use case. But within cloud, the kind of machine configuration, are you deploying it on a single GPU, are you deploying it on some CPUs or some GPUs? If GPUs, what kind of GPUs, if you know what I mean. So they go to that level of details, and you can have something called offsets. So you can basically determine the kind of hardware you are expecting to deploy this to, and they take care of optimizing your model, be it a CNN, be it a transformer, be it RNN, anything. They are actively working on adding more and more functionalities, more and more layers into their system so that they can optimize it for you. So that's the first thing, which is to export your model into these and then go through the optimization. You can also do in-house optimization. So I mentioned mixed precision training, which kind of touched upon the point of, hey, we can do away with 32 floating points for one parameter of the model. On the same idea, there is something called quantization of models. So the idea is, let's say your model is a just a fully connected neural network, and it has a total of 10,000 parameters. So 10,000 connections between neurons. All 10,000 of them are float 32 points. So quantization basically attempts at reducing those float 32 uh, parameters into float 16 or maybe even int 8. So tries to basically reduce the precision of these parameters and see how much are we trading off accuracy for that. So sometimes you might really be desperate to have a high performant model in terms of very low latency, very fast, even if it's not as accurate. So then you might consider quantizing. Here I have to mention chapter 19 again, PyTorch and Hugging Face. Hugging Face has a library called Optimum. So just like Accelerate is all about optimizing your model during training using the hardwares optimally, Optimum is the counterpart for deployment, in my opinion. I might be wrong in paraphrasing that, but Optimum is everything around deployment. Optimum also supports ONNX conversion from PyTorch to ONNX and from ONNX to hosting your model into ONNX runtime, OpenVINO, but it also provides methods to quantize. In chapter 19, we have a section where we quantize our CNN model, and in that case, it remains for you to be seen what happens with the performance, but you have an end-to-end running exercise where you can go use Optimum to quantize your models with few lines of code, if not one. So that's just on the just a side note on the optimization. Another piece on optimization would be, if you were specifically deploying your torch model on mobile, there is this whole library called PyTorch Mobile, and we have a brand new chapter in this edition, chapter 14, which is about building PyTorch mobile applications. So there is a method called torch.utils.mobile optimizer, and that is also a way for Torch to figure out what is the best um, combination of operations to keep, and how to move things around in the matrix multiplication, so to speak, for different mobile environments. So make sure to also check out that in chapter 14 in optimization. Once we have done exporting, once we have done optimizations, we are ready with the runtime, right? Typically for deploying your models, you want to consider one of the several options. So one option for any data scientist would be Flask or Django in Python, like all of these native Python web services, right? So Flask is really common with people, and chapter 12 in the book has a full end-to-end example on Flask. You could even consider something more sophisticated, which is Torch Serve. It's like a inbuilt hosting server within PyTorch. So you can, again, chapter 12 does go into the details of using Torch Serve. The benefit of using Torch Serve would be everything is handled by that piece of software. So if you want to launch two different versions of the same model, Torch Serve basically needs you to just provide that argument that I'm launching this version versus that version. You don't have to write specific code for all of that. It also does a lot of logging for you and so on. So while Torch Serve arguably is not as good as TF serving or TensorFlow equivalent, but I still love it. I use it as much as I can, unless I have a more complicated setup where I must use something like a Flask or a Fast API or a Django to basically host my model. You could also obviously go to cloud services straight up, because all of these AWS, Azure, GCP, they all have now native support for PyTorch models or deep learning models. So it's very common now to just use SageMaker straight up, for example, or I think it's called, in GCP we have a similar thing. It's missing, Vertex AI, I think. Yeah, Vertex AI. So there are different components in all of these cloud providers where you can just take your model with the optimized runtimes, and then you can just host them. And once you have figured out your deployment environment, of course you need to use something like a Docker and Kubernetes maybe stack to orchestrate your Docker environment. So Docker is basically to containerize your application. We have Docker discussed in full breadth and depth in chapter 12 as well. Make sure to check out. And then Kubernetes, we have not discussed Kubernetes, maybe something for the third edition, Bhavesh. So and so that's the normal stack of just getting things ready for deployment. Once you are there, the next few things I would say are things which we have not discussed in the book, but I just want to quickly mention so that we have a full picture. So there is CI/CD, so just to automate the testing, the building, and the deployment of your model. So here we are talking about things such as GitHub Actions, Jenkins, TeamCity from JetBrains, or GitLab CI/CD. So once you have this CI/CD pipeline running, it means that you have a repository of your training service, and you can make changes, you can create PRs, you can merge your code to master, and it automatically runs tests. If everything goes through, it uploads a build, it triggers a deployment. So your entire pipeline is sorted. And once you are at that level, you must start thinking about monitoring and logging of your services. So there is Prometheus, Grafana, there is the Elk Stack, the Elasticsearch, Logstash, and Kibana. So just to make sure you have your visibility or observability on your model performance. Is the block rate too high? Is the accuracy correct? uh, what's the latency on the 99 percentile? So all of these engineering, and also the data science metrics on your models. So that's very important. And to also add to that, the security aspect. So making sure we have the basic auth on the RESTful APIs that we have built around your service. Um, and just to make sure that your model is secure, adding something like Snike for vulnerability detection, so that if there is a dependency in your ML service, um, and there is a vulnerability in that dependency, you make sure to upgrade or patch that vulnerability, because more often than not that could cause problems, given how rapidly fast moving our entire AI community is. And one of the best recent examples is the NumPy upgrade, the major upgrade, which basically had so many backward incompatible changes that if one of your internal dependencies automatically switched, it would cause terrible nightmares. So making sure that you have all of that sorted. And finally, documentation. So something data scientists and machine learning engineers should really be proactive on is to basically then make API docs, usage examples, and so on, so that anyone else who is working on that model from there on is also able to work off your work. So hopefully that covers the deployment scenario really, like, as much as possible end to end from my side.
Yeah, that's very comprehensive. Oh, Ahmed, yeah, I'll if you message me after the session, I'll try and connect you with our sort of help desk um, with your issue. We've got time for one more question. So
Sure.
I'm just thinking, can we use PyTorch for cutting edge generative AI such as LLMs and diffusion models?
Sure. I don't know if people listening right now know that so GPT-3 or ChatGPT, that basically blew up AI for everyone in the world, that around like 22 2022. So GPT-3, GPT-2, and GPT-4, all of these, like, the most, like, rock star AI models of today, they are all written in PyTorch. On the one hand, on the text world, like the LLMs, which everyone is now like aware about, and they find it synonymous with generative AI. The other side of generative AI being, remember those diffusion models when we started seeing like those AI generated beautiful images, and one of the key players there, stable diffusion models from Stability AI, are also all written in PyTorch. These are like two of the biggest examples I can think of in today's generative AI landscape, of the two different modalities, images and texts. And this firstly just shows you that obviously PyTorch is 100% capable of delivering or enabling you to build those cutting edge, truly cutting edge models of today, like whatever is the state of the art today, you should be able to do that in PyTorch. And yeah, I mean, also some of these players are active contributors to PyTorch. So if they find something really, if they build something novel around, let's say they want to have a slight nuance difference in their implementation of a layer of a model, they also add it then to the Torch repository. So that's how beautiful the landscape today is for Torch. So absolutely it is usable. And as when it comes to, like, in the book, where do we discuss about LLMs and diffusion models? So I want to just give a shout out to chapters 5 and 7, where we have used Hugging Face transformers library to basically build language models, and also to use GPT-2 and GPT-3 models to generate text, and how to do that. And chapter 19 is obviously about PyTorch and Hugging Face. So we do speak a lot about how Hugging Face enables you to use different LLMs. So we also show how we use the T5 model from Google, for example, to run text generation. And on the other side, on the diffusion side, we basically have a fully dedicated chapter, this time chapter 10, I believe. And that's basically us building a diffusion model from scratch using PyTorch. And it literally emulates the philosophy of Stability AI to build stable diffusion. And it uses Hugging Faces diffusers library. So Hugging Face, I have mentioned this too many times, but again, to kind of bring back and just consolidate, transformers from Hugging Face is everything text, so state of the art. And diffusers from Hugging Face is everything around the diffusion or the image generative AI. And these two are so tightly knit and so well worked together with PyTorch that you should be able to use them to build your LLMs or your image generative AI models, as you will also see in chapters 10, 5, 7, and 19. And then obviously, just to complete the Hugging Face scenario, we also have the Optimum and the Accelerate libraries. These are more for MLOps, or for optimizing your training and your deployments. So again, we have enough content in the book to showcase to you that it's 100% possible to build the most cutting edge LLMs, the most cutting edge generative AI models on the diffusion or the image side. What actually is my advice is to actively be engaged in this kind of a community, to keep an eye on Hugging Face spaces or Hugging Face models, to even look for something better than what we have now. So I'll be honest here, and Bhavesh might not like hearing it, but uh, I have written a book. Books uh, get published in cycle of months, right, if not years. And the rate at which things are developing right now, it is we are talking about cycles of weeks. So within a week or within 2 weeks, for sure, massive updates happen. So while this book, I would say I have tried my best to keep the content stand as much as possible the test of time, as much as there is a strong wind of changes coming, positive winds of changes coming in the field of AI. The best way is also to keep in touch through different places available. I will just wrap up the answer to this question on LLMs and generative AI by going back to the point of PyTorch is now a part of the Linux Foundation, and there are these big players in AI who are active contributors and members. One of them is NVIDIA. NVIDIA has not so long ago launched Nemo, which is its framework for building LLMs, and it is a massive framework, and they are incrementally releasing more and more things. I think 1 week ago they released something called Nemotron 4, which is a model to kind of help you train your own LLMs and so on. And if you go to the GitHub repository of Nemo from NVIDIA, it is written in PyTorch. So yeah, the best stuff right now that is being built within the generative AI community, within the AI community, the most cutting edge things are also being written a lot in PyTorch. So this is like my main message, which is to, if you are familiar with PyTorch, if you are great for you, and it's a great time to be a part of this community. And if you are not, or if you don't feel confident enough, I think this book is really like meant to bridge that gap. And I said this the first time I was writing the first edition. I want to write it in a way which really has an easy learning curve, because I do not use fancy mathematics. You won't see much symbols around, but you will see code, which is obvious, which is what you have to do at the end, and it also helps you. And not a lot of code, because a lot of that is in GitHub repository, but some in the book. But a lot of simple language to just understand, explain, and understand the concepts behind all of what we are calling today as AI. A lot of this is really intuitive, understandable, and I am thankful to a framework like PyTorch to exist today, which makes it really easy for me to even like implement such a crazy amount of like AI models that are coming up today.
Uh, I'm just conscious of time. We have one question
Sure.
for Shipian. I don't know if we could squeeze that in for in 2 minutes before we do a final draw, raffle draw.
Okay, so architectures are hard to understand as an intermediate. Replicating research paper, although written in PyTorch, can be hard to navigate. What is your approach in building such architectures? Okay. Firstly, full honesty, I think there are maybe more than 100 really good papers coming out every week. Really good 100 papers coming out every week on archive within the field of deep learning, and I am not on top of them either. Okay, but I do try to read the most crucial papers in between. So like, you do get the most prominent papers coming your way through somewhere, like maybe through your LinkedIn feed, your Twitter feed or something, and you do get to know about them, and then you read them. So I fully empathize and I fully relate to it as well. So sometimes architectures can be hard to understand. The best way is to think in building blocks, um, which is also like a feature of PyTorch. It is very modular in nature. So trying to think in modules rather than going to the final depth of the details. Like, let's say a new paper came, and the only new novel thing that they brought about was changing ReLU to leaky ReLU and so on. um, like again, that is, while it's impressive that they made maybe improvements in the results and so on, for me that's not a solid enough paper for me to go and read and definitely understand. What I try to do is, if something really groundbreaking happens, so I'll give an example of going through this recent paper around using LLM as a judge to incrementally improve LLMs. And so what is more interesting to me is not the exact architecture of what they did, but what is more interesting to me is the concept behind it. And then if you really want to go deeper, you will have to do the hard job of either going through the details in the paper or going to the code base. I can only also give you one more pointer, which is, um, sometimes you can, there are tools to visualize the model. So if the model is not too large, shout out to Netron. So if you Google Netron, you can open an amazing web app, so you can just upload your model binary and visualize what's happening under the hood. With some experience, as you go deeper into reading model codes, if it is done well, if the repository is done well, you will also start understanding how different modules are placed, what parts are they using from scratch. So you have to remember that most of the works that are being done today are incremental. A lot of transfer learning is at play. So it might look daunting to you that there is so much code written here, but a lot of that is just previous work and then they are just building on top of that. So it's a hard thing to answer. I'm just going to be real. There are levels to this. The first level is to just understand what has improved here conceptually, what have they done. So have they changed something in the layers, have they changed fundamentally the structure of a layer, have they just worked around the optimization scheme, or have they just used a different data set. I know it's not as simple, but trying to compartmentalize makes things easier. And then there are levels to it. Again, if I, for example, when I had to write new chapters for the second edition, if I had to build a chapter for diffusion, and I will be honest, I did not really go into the depth of how diffusion really works. I knew you go from random noise into full image, but how? And to do that, at some point you need to go deeper into the code, because then I got to write some code for you to understand and build on top of. So yeah, there is no easy path to that. The only thing is go hierarchical in your understanding.
Excellent. So we'll just finish off with the final draw. Um, so good luck, everyone. So the winner is Venu. So if you message me on LinkedIn, message me your email address, and I'll get an e-copy to you as soon as possible. So
Congrats, Venu.
congratulations. And yeah, I think that's it. Thanks, Ashish, for your time. It was a great
Thank you
talk.
so much, Bhavesh. Thank you to everyone who kindly listened to this for an hour. I hope this was of some value. Thank you again for joining from all time zones. Thank you to you, Bhavesh, and I hope you guys get a copy of the book and hope it
Yeah.
turns out to be useful for you.
Right,
Until the
thanks,
next.
everyone. Bye.
Bye.